Okay, very well. I suppose I'll start then. I welcome the viewers to this problem solving and live interaction session for the subject strength of materials offered by Professor K. Ramesh on the Swayam portal. So today we are meeting after 2 weeks actually, but I had uploaded the video. So today we'll be discussing the contents of week 8, which has to do with bending stresses, essentially the starting of bending stresses. Undo. Okay. Okay, so before we begin, are there any questions? Is the assignments going fine? Do you want me to explain anything there? Are there any doubts or questions, anything like that? If there are, you please feel free to post them or unmute and ask, or you can also type them here. In the meantime, let's get started. So before we begin, I'll just introduce myself to people who are watching this for the first time. My name is Ganesh Ramaswamy. I'm a doctoral scholar in the Department of Applied Mechanics and Biomedical Engineering, working under the guidance of Professor K. Ramesh and Professor U. Saravanan from the Civil Engineering Department. So once again, I welcome you to the session. So let us look at the first question. When a rod or a slender structural member is subjected only to transverse load, it acts as a what? Is what is asked. So essentially what we are looking at here is, let us say that I have a section like that, which has a slender structural member, meaning one of the dimensions is much more than the other two. Basically, if you are looking at 3 dimensions, so one of the dimensions far exceeds the other, which makes it a very slender member. Something to that effect. If this is a slender member, this is the axis of that member. This is the axis of that member. Now, granted, there are no constraints as to how this can be loaded. We require slender members for our components, but this can be loaded in any way. For example, if a member is loaded like that along its axis, then we call them as axial members, which are essentially bars. Hi, good evening, Mr. Jaykrishnan. I'm audible clearly, I hope.
Good evening. Yes.
Good evening. Yeah. So when we have a slender member and when we load it along its axis, so these essentially are, it could be tension or compression as we saw in truss members. So these are basically referred to as bars. Now let us say that we load the same member with a twist instead, which is denoted by a double-headed arrow, which implies a twist along its axis. Then this, we name it as a shaft and we do the analysis appropriately. For the same member, let us say I take the same member, but now I do not apply the loading along its axis. Let us say I move it here. I do not apply the loading along its axis, but let us say that I load it at some angle. Or rather, let us say that I have transverse loading that is perpendicular or at any arbitrary angle to its axis. So one of its components, if there is a load that is applied like that, one of its components will get resolved into an axial pull or push, compression or tension onto the member, and the other one would essentially be transverse to the axis of the member. So when it is transverse to the axis of the member, it behaves as a beam, which implies that it bends. So a member which is subjected to forces like this, inclined forces like this, let us say, will result in the member having axial pull as well as transverse loading, in which case it is acting as we will club the behaviors then. If it is compression, we will call it a bar column strut, and if it bends, it will become a beam column and so on. So presently we are looking for structural members where the loading is only transverse to the axis of the member, which are referred to as beams. So these are bars, these are shafts, and these are beams. So far in our earlier analysis, we saw in truss analysis, how do we go about finding out forces in the bars. Once we found out the forces, initially in our discussions, we saw that once as a member is subjected to an axial load of this much, how to calculate the stresses and deformations. Basically, we have the stress as just our strain into epsilon, strain into E. So we saw this expression, the change in length as PL by AE, which was applicable to bars. Then we switched to torsions, twisting of shafts, where we had the torsion formula where our stresses were related to the uh, twisting moments using the torsion formula, which is mt by G as tau by R as uh, mt, no, G won't come here, mt by J, actually I mean polar moment of inertia, IT, and then we have phi by L, G phi by L. So we saw this in the week previous to this, where we had the torsion formula and we saw how to calculate the stresses in these bar given a twisting moment, how to calculate the stresses as well as the twist or the shear strain in another form in these bars. Now we move on to members that are basically subjected to axial transverse loading, which has nothing but beams. So we will see how to calculate the stresses and deformations, but beams becomes a bit elaborate. So stresses and deformations, we will not combine it and study it at once. First, we will focus alone on the stresses, and then we will move on to uh, deformations in the form of deflections, which is an entire week dedicated to that. So presently, we will be looking at the bending formula, essentially, or called the flexure formula, which is a bending by I, Z. This is bending about Z, I, Z, Z equal to sigma x by y equal to, sorry, E by the radius of curvature can be represented as R or rho or whatever. So this we are looking at the flexure formula in one of the planes. When it becomes a multiplanar problem, that is bending moments act about multiple planes, then we will just simply use the linear superposition and superimpose the results in order to get us what we want, which will also come under the purview of unsymmetrical bending, which we will study later. But the basic stepping stone of this happens to be the bending formula, which in its simplest form is this. So we will see how we apply this in order to find, given a bending moment, and we have done enough exercise to find out bending moments for given loaded beams. For example, even in our engineering mechanics courses, we saw a beam which is subjected to bending a load of a particular kind. How do we find out the bending moment variation along the length of the beam? Basically, we sketch the bending moment diagram for that. The purpose of the bending moment diagram is, given a section, if I want to find the stress there, I should be immediately able to, I should have some way to immediately pick out what is the bending moment at that point, which is what we essentially do using the bending moment diagrams. So we have seen elaborately how to draw these. So here we will be looking at how to calculate our stresses and essentially curvatures. So 1 by R is nothing but our curvature. Curvature is related to strains. But how this deforms and what is the deflection, that we will be seeing it in another week to follow, which is quite elaborate. So we have broken this down into two parts. So with this preamble, if I were to revisit this question, when a rod or a slender structural member is subjected only to a transverse loading it acts as a beam. I hope that is clear. Granted that we analyze these separately, but essentially in components, it is not necessary that the members have to be subjected to only either one of them. So there could be a combined loading as well. So that is where our principle of superposition comes in handy, and we superimpose results, compare it to one standard failure theory from uniaxial tension, and find out what is the factor of safety, and go about designing the members, which is something we will also see as we go along in the course. All right. So this question says a beam is said to be under pure bending if it transmits what? Only a constant bending moment along its length, linearly varying bending moment along its length, both bending moment and shear force along its length, constant shear force along its length. So why are we looking at this pure bending case? So if we see what we have derived in the lectures, the flexure formula is derived. I'm refraining from deriving it again here, threadbare. If you want, we can do it perhaps in the next session when we go into deflections. There, initially, in order to develop the moment curvature relationships, I'll be deriving that. So I think we will cover it there. So I won't be delving much into that now. But I'll just give a brief on why are we looking at this. So let us say that it's an idealization that we have two loads applied like that, which are equidistant, so to speak, in a simple beam. So let us say that I have a beam like that, which has a roller and a hinge at the other, and it is subjected to this kind of loading. So we know, let me draw one. And let this be the bending moment sign convention. I'll just add a page here. Yeah. Okay, so let me take this beam here. Sorry, 1 minute. So I have a beam like that with sign conventions as given here. So we know for this beam, if I were to draw the shear force diagram and let this be A, let this be some 2B like that. So for this, the shear force diagram will be like this. I hope there is no confusion as to why it will come out to be this way. If there is any confusion, please let me know. And then the bending moment diagram will be something like this, where this is this magnitude. This is PA. If I call this P, let that be A, and this is nothing but plus P. So in a beam like this, in a 4-point bend beam like this, essentially what we have, there is a reaction which transmits a constant shear force, this portion. Then it is nullified by, then for this portion there is essentially no shear force acting here. Then we have a drop in the shear going back, and the reaction brings it back to zero. So we have the shear force diagram like this with my sign convention. I should put it here. and my bending moment diagram is like that. So what we observe here is in this portion of the beam in between the loads, and of course we are looking at sections that are sufficiently far away from the loading point so as to not go into stress concentrations and things like that. In this portion, when we see the deformed structure of the beam, this beam will deform something like that. What we notice is in this portion that comes in the middle of that beam, where there is no shear force acting, it bends as a circular arc. The shape of the deflected curve is actually an arc of a big circle, which is of radius r, which is this r. This is that r. So essentially what we note is our flexure formula, which we apply throughout this course, is actually valid only when the bent curve is part of a circle with a constant radius of curvature. This gets violated when we go into sections where there is non-zero shear force. In sections where there is a non-zero shear, the arc will no longer be a circle but a higher degree curve. It is because of this reason that our flexure formula is not strictly applicable there. But even if we were to apply it there, the errors are not too high. So, which is the solace, which is what we will be resorting to in this course. We will be applying the flexure formula to all the sections of this beam in order to analyze this. However, strictly speaking, the flexure formula is only applicable for the portion where the shear force is zero, where there is no change of where there is only pure bending. Here we can see that it is subjected to a constant bending moment. Whereas as soon as we have some shear, we can see that there is change in the bending moment because of one relation which we also saw in engineering mechanics as dm by dx is v. So once we have a constant shear force, which means the slope of the bending moment diagram is constant. We want the slope of the bending moment diagram to be zero in order for applying the flexure formula with uh, mathematical rigor. In other places, it is just an approximation. We are just approximating the results, but that is reasonably good, reasonably acceptable in this course. We will see how to go about solving those cases in the next level course. For the present course, we will be focusing our attention on this. So this is the reason why we want to find out if our beam is subjected to pure bending or not. If it is subjected to pure bending, the solutions that we are getting from applying the flexure formula to this beam are exact. Otherwise, they are an approximation, which is why we term it as an engineering analysis of beam instead of a rigorous exact analysis. I hope that is clear. So this portion is what is called is what is subjected to pure bending, which means no shear and a constant bending moment. So a beam is subjected to be under pure bending if it transmits a constant bending moment along its length, linearly varying bending moment, both bending moment and shear force, constant shear force. We see that a constant shear force implies a constant slope of the bending moment diagram, which means a varying bending moment, which is not the case of pure shear. I hope that is clear. So let us look at the next question. For a beam having a square cross section made of a single, yes, please. Voice is not much clear. Okay, minute. Are others also facing this issue? Could I get some feedback, please?
Appears fine to
Fine to
me.
me. What about Mr. Praveen? Could you kindly confirm? Or Miss Monty?
It is okay,
It's
sir.
okay. Okay. Then what I suggest is, Miss Monty, could you just leave the meeting and rejoin? Maybe there is some issue there. I'm not very sure. I'll wait. You can just leave the meeting and rejoin. Perhaps that is the issue. Because yeah, because at my end it seems everything seems to be fine. at 100%. Okay. Okay. Are you able to hear me clearly now, or this issue is still persisting? Because I suppose I have checked everything at my end, and the other participants also seem to be hearing me all right. Could you just confirm if my voice is still breaking? It's okay now? All right, great. Fine. Okay, so we saw why we need to study if a beam is under pure bending or not, and what essentially pure bending means. So let us look at this question. For a beam having a square cross section, so what we are saying, we have a beam. So let me draw the beam. This is a slender beam, and in this course we are looking only at slender beams, not at deep beams. A slender beam means this length, and let me take a section here. When I view this section, I'll be seeing something like this, where this is the width of the beam and this is the depth of the beam. I'm just taking the example of a rectangular beam presently. So when L is much greater than the largest lateral dimension, whichever is the greatest of B or D, then this we term this as a slender member. Okay. So for a beam having a square cross section, so let me just put both of these as A. Let this be A and let this also be A. Yeah. And it is made of a single material. The neutral axis will coincide with which of these is what is asked. Essentially, the neutral axis is a fiber is so what we mean here is we take a slender member. These are made up of multiple fibers that are stacked together, let us say. So when I bend this, let me take a section over here and let me blow up that section so that it is of considerable depth here. So let this be the section. This is before bending. And let this be its shape after bending. Roughly speaking, let it be something like that. So if I were to take, let me call this fiber 1 and let there be a central line like that. Yeah, let this be the other curve. What we mean by neutral axis is there is essentially a fiber in this beam subjected to pure bending that doesn't undergo any change. So if we see the fiber 1, if we compare the lengths, we will see that the length now in the deformed configuration when this we are looking at after bending has reduced because of compressive stresses. At the same time, the bottom fiber has stretched. So if this has reduced its length and this is increased its length, so naturally there has to be some point where there would be no change in length because it is shifting from positive to negative, so to speak. So that point where there is a fiber which does not change any length, that is what we refer to as the neutral axis, which is only present in the case of pure bending. It will not be present where there is shear, but we will still approximate that it is there. That is why we call that as an engineering analysis of beams. But it is very essential that we understand this fact about the assumptions that we are making, that it is not a rigorous analysis. We are only approximating in cases where shear is present. Wherever shear is absent, our analysis is exact, and the arc of this arc would actually be a circle in such a case, which means if I were to connect this will connect at one point where the entire beam will have a common curvature. I hope that is clear. So this is what the neutral axis is. What we will see in the case of a homogeneous section, meaning it is made of a same material, where it follows that in a homogeneous material, section, the neutral axis coincides with the centroidal axis. Now, why is this so? If we look at the derivation, which I will perhaps do it in the session where we are trying to find displacements. I suppose it is the next one or the one after that. When we actually look at displacements, so there I will be deriving these expressions threadbare, so that becomes clear. But why this happens is it's a consequence of our equilibrium equations. So when we subject a beam to pure bending, it means that it is not subjected to any axial force. So when we add up the axial forces, what we see is that there is a point about which when we take the moment of that area, first moment of area will come out to be 0, which implies that that point where the tension to compression transition happens actually coincides with the centroid of the member. And we just from our previous discussion, we know that wherever tension to compression transition happens, at that point, the neutral axis lies because that doesn't change in its length. It experiences no change in its length. When we superimpose these two facts, it happens that our neutral axis will pass through the centroid of the cross section, with the only constraint being that it has to be a homogeneous cross section. Now, if this material was different and this material was different, this will no longer hold true, but we have special ways to deal with such materials, which will perhaps come in the following weeks. Presently, we are just looking at the first steps to bending. So this is something to be kept in mind, that neutral axis of a homogeneous section will pass through the centroid of that cross section. In other words, the centroidal axis of that cross section will not change its length under bending, under pure bending. This is the consequence of, this is the conclusion we can draw from that. I hope that is clear. So, for a beam having a square cross section made of a single material is what we are emphasizing here. Single material meaning it is homogeneous. subjected to pure bending, the neutral axis will coincide with the centroidal axis of the beam's cross section. Since this is a square, it will just be the axis passing through the midpoint of the depth. I hope that is clear. If there are any questions here, I am happy to take them. Or if there are at any point in time, you please feel free to bring them up. I'll try to address them. All right. So let us look at this question. The plane perpendicular to the plane of symmetry through which the neutral axis passes is called what? So we saw that this in the cross section, if we see, let me draw it here. So if we say that this is the plane, in the cross section, we have a plane like that. And in the longitudinal section, when we look at it, it looks like this. So when one is named the axis, the perpendicular plane to that is named as the neutral plane. There are certain books which will reverse this. They will call this the neutral axis and this as the neutral plane, and so on. But the essence is how it intersects. If neutral axis intersects with that plane, we call that the neutral plane. So it is one and the same. But why is this important? It is because we are looking at one surface of that beam. We are not looking at all the surfaces of the beam, because naturally when we see here that there is tension and there is compression. So if there is tension at the bottom and compression at the top, the shape of this square section will no longer be a square because of our Poisson's effect. So it will be something like this. I'm just exaggerating it because the nature of strains are compressive at the top because of Poisson's effect. This will stretch out, and because it is tensile, it will compress. So this is how the cross section will look after it has undergone the bending. I'm exaggerating the figure, but we do not apply our equations in this. We still apply it to the rectangular section. Essentially, we are looking at only the plane of symmetry of this section, and we are applying the analysis there. Granted, these effects are there, but these are second order effects. The main response of the beam we capture by cutting the central plane and applying the bending equations. So that is why this question is asked. Essentially, we should know which plane we are cutting into. Let us say that we did not have symmetry about this plane. For some reason, our cross section was like that. Then this will no longer be analyzed using our simple bending analysis. This will go into the purview of unsymmetrical bending, which we will see in the weeks to follow. But presently we are focusing on prismatic sections, which have a symmetry about the neutral plane. I hope that is clear. Okay, so let us look at this question. Yeah, as I was just discussing, this shape has come about because of the Poisson's effect, as a result of the Poisson's effect. Consider a beam subjected to pure bending as shown. The curvature at the top portion of the beam is indicated in the figure is called what? Is it anticlastic curvature, synclastic curvature, helicoidal curvature, or cylindrical curvature? So what we see here, let me take a small section of this and blow it up. So let me trace one line here, one curve here, like that. So what do I see? That if I try to locate the center, it goes somewhere towards the top of the beam. Now let me draw another curve along this section. If I try to locate its center, it is somewhere this way. So essentially both the curvatures are opposite in nature. One has a positive curvature while one has a negative curvature. So this is referred to as anticlastic curvature. In cases where they have a similar type of uh, either both are positive or both are negative, that will be referred to as synclastic curvature. It comes from coordinate geometry. Let us not delve much into that. But the essence of this is that this bulging comes about, and it is also shown using an experimental result in the lectures if you revisit it. Using a very soft beam, when we bend it, we'll actually be able to visualize these curvatures at play. Although our bending equations are not applicable for the amount of bending that is shown in the lecture with that soft beam, it is just to bring out the essence that curvatures do happen, do come about, and comes about in this way. And this effect, which we are seeing, which is along the thickness of the beam, this we do not consider in our analysis. Presently, all our the bending formula which I wrote here, the R we are looking at is at the central plane, and it is this radius. It is this radius. So this is what we are looking at the center cut of the beam. That is what we are interested in presently. But it is also important to know what happens in a plane that is not falling. So a 3D representation of that gives you a better appreciation of this thing. So this is anticlastic curvature. So are there any questions at this point? Is it clear what we are discussing? Okay, I take it is clear. So when red has a negative curvature, why? Because it is concave upwards. Concave upwards is negative in mathematics. That is what we use for our maxima, minima, that double derivative test. This is essentially we compare the curvature to whether it is flat or curved downwards or upwards. By that only we derive which is maxima, it is either a maxima or a minima. So that is a negative curvature, and this is a positive curvature. When both along two perpendicular directions, the curvatures are of opposite nature, it is known as anticlastic curvature. All right. So a canopy is a type of construction that are built to provide shelter from sun and rain, as shown in the figure. So we see here that we have a wall, and this frame is essentially clamped to the wall by some means, and it is projecting this way. So there are members like this, number of members, and then we have a cloth or some covering over that, which actually serves the purpose of protecting, providing the shelter and so on. Identify the type of beam used for the construction. So we just have to identify whether it is a simply supported beam, an overhanging beam, a fixed beam, or a cantilever beam. So here we can clearly make out it's not a simply supported beam. That's fine. Whether it is a fixed beam or a cantilever beam, fixed beam is again fixed at both ends. That is how we name it. So it is not a fixed beam. But one might argue that this is an overhanging beam. Why do we not call it an overhanging beam? Essentially, if we were to see if there was a beam projecting out of the wall and going through, then it would have been termed as an overhanging beam, meaning that it is presently having zero fixity it is presently having fixity at this point. If that was not so, it was just supported over a prop and hanging out, then it would have been an overhanging beam. Which means if rotations are allowed here, it becomes an overhanging beam. If rotations are not allowed, it becomes a cantilever. So we can see that it has been clamped to the wall. as a separate entity. There is no continuity of slope.